MATU 206 Week 3, Chapter 3, Parts 1 through 3. This week we'll be looking at a lot of properties. First one we look at is frequently the most confusing, or one of the most confusing for my middle school students, the closure property of addition of whole numbers. That means our whole numbers are 0, 1, 2, 3, 4, and so forth. To be closed, you need to be able to take any two values, any two of these whole numbers, add them together, and get another whole number. Well, it's true for the addition of whole numbers, because any whole number you take, 2 plus 3 equals 5, another whole number. 4 plus 83, both are whole numbers. You add them together, 87, that's another whole number. So the closure property implies the sum of two whole numbers exists and that the sum is a unique whole number. Students get confused because closure property does not exist for a subtraction. So we have closure for subtraction of whole numbers does not exist for the reason that 1 is a whole number. You can take away 2, which gives us -1, which is an integer, but not a whole number. Students have trouble with this concept. Commutative property. I like to explain commutative property as being the root word commute, as in to travel from one location to another. So if A and B are any whole numbers, then A plus B is the same value as B plus A. A traveled, then they swap places. So if you have 4 plus 7, that will be the same value as 7 plus 4. That's an example of the commutative property of addition of whole numbers. Students wonder if commutative property holds true for addition. Well, if we have, or subtraction rather, if we have 4 minus 7, is that the same value as 7 minus 4? Well, 7 minus 4 on the right side of the equal sign is 3, but the difference between 4 and -7 is a -3, so the commutative property does not hold for subtraction. Associative property of addition of whole numbers. If A, B, and C are any whole number, then A plus B plus C is the same value as A plus B plus C. So let's try it. 3 plus 4 plus 5. If we associate those, will that be the same value if we do associate those? Parentheses say take care of it first, so 3 plus 4 is 7 plus 5. Is that the same value as 3 plus 9? It is. Doesn't matter what order you add numbers in, you will still get the same value. That's what it's, or not order, but how you group them. Associative property has to do with grouping. Does it hold true for subtraction? Is 5 minus 7 minus 4 the same as, if I do this, is that the same as 5 minus 7 minus 4? 5 minus 7 is -2, minus 4, we get a -6. Is that the same as, let's see here, 7 minus 4 is 3, and 5 minus 3 is a +2. They are not the same. There is no associative property of subtraction. Identity property. What can you, of addition, what can you add to a value and that value still maintains its identity? Its identity does not change. You can add 0. So A plus nothing is A, and that's the same as nothing plus A. So you can add 0 and not change the value of the value you started with. Does it hold true for subtraction? is a minus 0. Well, of course, that is a, but is that the same as 0 minus a? Notice that we're taking a away from 0. A does not have the same value as negative a. So there is no identity property of subtraction. The left to right algorithm for addition. This is just another possible way to teach addition. If we were to do it the traditional way that I learned in school, I'd do 8 plus 7 is 15, and then I can't put 15 there, so I carry a group of 10 next door to the 10, so I have one group of 10, and 1 plus 6 is 7, plus 5 is 12, but I can't put 12 there. I can only put a single digit there, so now I carry 10 groups of 10 next door, and 10 groups of 10 is 100. So 1 plus 5 is 6, plus 7 is 13. And technically, I should just say I have to take 10 groups of 100 next door, and that's how I get my 1 in the thousands place. Well, this left to right algorithm for addition kind of does away with this carrying and all these little ones up in the air. And what they do is they just say, okay, we have 500 plus 700. 500 plus 700 makes 1200, and we're in left to right algorithm for addition. We're recognizing place value, which is an important skill that when the students get to me in middle school, they really don't know place value. They know this algorithm to add, but it divorces the numbers from place value, so they're kind of lost. And now 6 and 5 are both in the tens place, so 60 plus 50 is 110. And 8 and 7 are both in the ones place. 8 plus 7 equals 15. So now here what we did is we took this 1200 and the 15, and since there's zeros there, we lumped them into 12, 15, and then the 0 and 5 doesn't change it, but this 1 and that makes this 1, so we cross it out and make it 2. This 1, cross that 2 out, make it 3, and then take the 1 from the thousands, this 3, this 2, and just bring them over there. So that's how the left to right algorithm for addition works. It'll probably never take over the traditional standard algorithm, but in some instances, some respects, I would like it to. The standard algorithm we learned is much more compact, and that's why it will probably win out. But this left to right algorithm really does bring place value in and has students recognize the meaning of place value. And that can be so important in middle school that unfortunately they don't have, and it's a struggle for me to get them to understand it. The lattice algorithm for addition is kind of a compromise between the left to right and the standard algorithm. What we're doing is we're just adding individual values without paying any attention to place values. So 7 plus 8 makes 15, but instead of carrying and putting the 1 up here, we just put it right there. So 7 and 8 makes 15. 6 plus 7, again, these are the 10s, so it should be 60 plus 70, but we ignore place value. And but 6 plus 7, instead of carrying the 1, we just put it there, so it's 13. 5 plus 6, here we go. This is the hundreds place, but again, we're ignoring place value. But 5 plus 6 makes 11, so we just put the values there. And 5 plus 3 is, again, in the thousands place, but we're ignoring it, is 8. But now, to get our sum, we take this 5, so we then add down through the diagonals, and that just gives us 5. We add down through here, 1 plus 3 gives us the 4. We add down across this diagonal, 1 plus 1 is the 2. We add down that diagonal, 1 plus 8 is the 9. And we add down this diagonal, it's just 0, so we don't need to write it. And that's how we add 3,567 plus 5,678 using the lattice algorithm for addition. Understanding addition and subtraction in bases other than 10. Well, this provides a little addition chart We're used to seeing go all the way up to 10 and down to 10, across and down to 10. But this is for base 5. Remember, in base 5, we only have 5 digits, which are 0, 1, 2, 3, and 4. There's no such thing as a 5 in base 5. 5 digits, and we carry a group of 5 when we're adding, when we get there, or when we borrow a group of 5 also when we're subtracting in other bases. But anyway, 0 plus 0 will be 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, 0 plus 4 is 4. 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, but when we do 1 plus 4, there's no such thing as a 5, so we have to carry to the 5's place. Also, remember, in place value, we have 5 to the 0, which are what we would call the 1s. We have 5 to the first, which are the 5's place. We have 5 squared, which, if we shuffle it into base 10, we'd say it's the 25's place. We have 5 to the third power, and we have 5 to the fourth power, and so forth off to the right. The decimal point would go there, and we would have 5 to the negative 1, 5 to the negative 2 as we proceed to the right. So when we have 1 plus 4, we can't say it's 5, but we say it's 0 in the 1's place, and we have one group of 5. So that's what this is all about. And if we were to add 4 plus 4, that's not 8. What it is it's a group of 5 and 3 1s, is how we have to look at this. So if we're going to add 343 plus 2 in base 5, 343 plus 2, when we add the 3 and the 2, in base 10 we'd say we have a 5, but there's no such thing as a 5. What we have is a 0 and one group of 5s that we carry next door. And then we have this 1 and the 4, which again makes a number that doesn't exist. It makes a group of 0 1s and a group of 5, which we carry next door. And then we have 1 plus 3 is 4 in base 5. To subtract 43 from 222, 2 minus 3, we can't do this, so we have to borrow. We have to take that and make that 1. But what are we doing? We're actually bringing one group of 5. So now that we have one group of 5, really in base 10 we'd say 5 plus 2 is 7, subtract 3 is 4. And then we can't take 4 away from 1, so we have to borrow 1 there. And now we have a group of 5 and 1 1. And 5 plus 1 is 6, minus 4 is 2. And then we have the 1, and that's in base 5. When I work in bases, I do slip back into base 10. Just try and, but that's the way I do it. Now we have some properties of whole number multiplication. The closure property is the same as in addition. Closure property multiplication. If we have the whole numbers, which are 0, 1, 2, 3, 4, 5, 6, and so forth, what the closure property says is we can take any of these whole numbers, any of them, and multiply 2 of them together. And if the closure property holds true, then we will get another whole number. So example, we can take 4 and multiply it by 5, which gives us 20, which is a whole number. Will this hold true for division? What if we do 4 divided by 5? They're both whole numbers, but will that result in a whole number? Well, 5 won't fit into 4, so we have to add the decimal point, and we get 8 tenths. 8 tenths is not a whole number, so the closure property of whole numbers does not hold true for division. The commutative property of multiplication. Again, the commutative property is from the root word commute, which means to move locations. So if A and B are whole numbers, then A times B will have the same value as B times A. If that's true, then we can say 3 times 6, will that be the same value as 6 times 3? 18 does equal 18. The commutative property does hold true. Is it true for division? Is 6 divided by 3 the same value as 3 divided by 6? Well, 6 divided by 3 is 2. Does that equal 3 divided by 6? No, because that's 1/2. It does not hold for division. The associative property of multiplication. Associative means you can multiply these three values in any order. So if we had 2 times 3 times 5, 2 times 3 times 5, but on this side we group the 2 and the 3, and on this side we group the 3 and the 5, will that give us the same value? Well, 2 times 3 is 6 times 5, and that would be 2 times 15. 6 times 5 is 30, and 2 times 15 is 30. It does hold for this for multiplication of whole numbers. How about division? Does it work? Can we say that 6 divided by 2 divided by 4 is the same, if we do this, as 6 divided by 2 divided by 4? Can we associate different pairs? Well, that's 3 divided by 4, which is 3/4. Does that come out to be, this is 6 divided by 2 by 1/2? 6 divided by 1/2 is 12. Does 3/4 equal 12? No, it doesn't. So there is no such thing as the associative property of division. So it's not for division. The identity property of multiplication of whole numbers. What can you multiply a value by that doesn't change the value? 1. The identity property of multiplication is 1. A times 1 equals A, which is the same value as 1 times A. Does that work for division? Does A divided by 1, A divided by 1 will be A. Is that the same as 1 divided by A? Is A over 1 equal to 1 over A? No, it's not. Those are different. So it does not hold for division. And the zero multiplication property says that for any value, A times 0 equals 0, and that's 0 times A. So it's kind of like the identity property, but the identity doesn't change the value. Does that hold for division? Well, A divided by 0. Do we know how to divide by 0? We say that division by 0 is undefined because we don't know how to take something and split it up into no groups. So there is no zero division property.